Good morning, good afternoon, and good evening, everyone. Today I'm going to talk about recent machine learning papers that you ought to check out that were hot off the press for this month. I plan to do these machine learning papers once every quarter or so. That way you have an idea of what can be applicable to the oil and gas industry, what's already applicable to the oil and gas industry, and what additional context you may need for some machine learning, especially the papers that I'm going to cover will be ranging from deep learning to multivariate regression, you name it. The first paper I'll talk about is Symplectic momentum neural networks using discrete variational mechanics as prior deep learning. In this paper, we introduced symplectic momentum neural networks as models from discrete formulation of mechanics for non-separable mechanical systems. The combination of such formulation leads to SIMOs to be constrained towards preserving important geometric structures such as momentum and symplectic form and learn from limited data. It allows to learn dynamics only from the poses as training data. We extend SIMOs to include variational integrators within the learning framework by developing an implicit root finding layer which leads to end-to-end symplectic momentum neural networks. Through experimental results using the pendulum and cartpole, they show that such combination not only allows these models to learn from limited data, but also provides models with the capability of preserving symplectic form to show better long-term behavior. I suggest you check out this paper because there are some applications to deep learning in the oil and gas industry, and they could be used for predictions like production forecasting, for instance. You can check out the code of this paper. I'll put that in the description box below, and I'll also send you the link to the paper so you can get a better idea of what this paper is about. But most of these papers that I get a lot of my information from are called paperswithcode.com. The next paper I'm going to talk about is HEAM, or High Efficiency Approximate Multiplier Optimization for Deep Neural Networks. To improve the latency and power efficiency of hardware accelerators by exploiting the error resiliency, they propose an application-specific optimization method for the automatic design of appropriate multipliers for deep neural networks. The proposed method optimizes an appropriate multiplier by minimizing the error according to the probability distributions extracted from DNNs. By applying the optimized approximate multiplier to a DNN, they obtain a 1.6, 15.32%, and 20.19% higher accuracies than the best reproduced approximate multiplier on the widely used MNIST, Fashion MNIST, and CFAR 10 datasets, respectively, with 12.7% smaller area, 23.38% less power consumption, and 16.53% lower latency. Compared with an exact multiplier, the optimized multiplier reduces the area, power consumption, and latency by 36.88%, 52.45%, and 26.63%, respectively. Applied to FPGA-based and ASIC-based DNN accelerator modules, the approximate multiplier obtains a low LUT utilization and small area respectively with the competitive max frequency and power consumption, which shows the effectiveness of the proposed method in reducing the hardware cost of DNN accelerators. Experiments on DNNs indicate that the generated approximate multiplier can achieve higher accuracies than other tested approximate multipliers by large margins with significantly smaller area, less power consumption, and lower latency. These results indicate the importance of application-specific design in approximate computing. Furthermore, they implement a toolbox named Approximate Flow to evaluate the accuracies of DNNs with quantization and approximate multiplication. Again, if you use any deep neural networks for your oil and gas industry applications, check out the code in this paper and check out the multiplier optimization for this specific application. The next paper I'm going to talk about is called datavec, a general framework for supervised learning in speech, vision, and language. While the general idea of supervised learning is identical across modalities, the actual algorithms and objectives differ widely because they were developed in a single modality in mind. To get them closer to a general supervised learning, they present datavec, a framework that uses the same learning method for either speech, natural language processing, or computer vision. The core idea is to predict latent representations of full input data based on a masked view of the input in a self-distillation setup using a standard transformer architecture. Instead of predicting modality-specific targets such as words, visual tokens, or units of human speech which are local in nature, datavec predicts contextualized latent representations that contain information from the entire input. Experiments on the major benchmarks of speech recognition, image classification, and natural language understanding demonstrate a new state-of-the-art or competitive performance to predominant approaches. If you have a tool that looks through investor presentations or looks through investor presentation speeches or speeches that are related to the oil and gas industry, this can be a useful code to look at the general framework of supervised learning in natural language processing, in vision, and in language. And I do see some potential applications in this in the oil and gas industry, especially if you're scraping different types of information that may not necessarily be written in text. The next paper I'll talk about is a correlated-informed neural network, a new machine learning to predict pressure drop in microchannels. So this is definitely for those that are focused in natural gas engineering. Accurate pressure drop estimation and forced boiling phenomena is important during the thermal analysis and geometric design of cryogenic heat exchangers. However, current methods to predict pressure drop have one of two problems: lack of accuracy or generalization to different situations. In this work, they present a correlated-informed neural network, COINN, a new paradigm in applying the artificial neural network, or ANN, technique combined with a successful pressure drop correlation as a mapping tool to predict the pressure drop of zeotropic mixtures in microchannels. The proposed approach is inspired by transfer learning, highly used in deep learning problems with reduced datasets. The method improves the ANN performance by transferring the knowledge of the sun and Mishima correlation for the pressure drop in ANN. The correlation and having physical and phenomenological implications for the pressure drop in microchannels considerably improves the performance and generalization capabilities of the ANN. The final architecture consists of three inputs: the mixture vapor quality, microchannel inner diameter, and the available pressure drop correlation. The results show the benefits gained using the correlated-informed approach, predicting the experimental data used for training and posterior tests with the mean relative error of 6% lower than the Sun and Mishima correlation of 13%. Additionally, this approach can be extended to other mixtures and experimental settings, a missing feature in other approaches for mapping correlations using ANNs for heat transfer applications. I can see this being an application to the oil and gas industry by looking at different pressure drop correlations, especially for pipelines. And if you think about natural gas engineering, there is a direct application shown in this paper. The last paper I'm going to talk about is TranAD, deep transformer networks of anomaly detection in multivariate time series data. The immediate application I can think of is more of production data. That's a time series data. Efficient anomaly detection and diagnosis in multivariate time series data of great importance for modern industrial applications. However, building a system that is able to quickly and accurately pinpoint anomalous observations is a challenging problem. This is due to lack of anomaly labels, high data volatility, and the demands of ultra-low inference times in modern applications. Despite the recent developments of deep learning approaches for anomaly detection, only a few of them can address all these challenges. In this paper, they propose TranAD, a deep transformer network-based anomaly detection and diagnosis model which uses attention-based sequence encoders to swiftly perform inference with the knowledge of broader temporal trends in the data. TranAD uses focus, score-based self-conditioning to enable robust multimodal feature extraction and adversarial training to gain stability. Additionally, model-agnostic meta-learning, or MAML, allows us to train the model using limited data. Extensive empirical studies on 6 publicly available datasets demonstrate that TranAD can outperform state-of-the-art baseline methods in detection and diagnosis performance with data and time-efficient training. Specifically, TranAD increases F1 scores up to 17%, reducing the training times up to 99% compared to baselines. When I think about time series, again, I think about production data, and this could be a potential application to the oil and gas industry when you look at the details of the paper, which I suggest you do. Those are all the papers I wanted to cover for today's video. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the YouTube platform so I can incorporate your feedback into future videos. Thank you so much for taking the time to watch this video, and I'll see you in the next one.